Hello. Today we'll be talking about ownership. We're starting off with chapter 4, and it's quite a heavy topic, so I made a little summary as always based on Steve's and Carol's book, which hopefully will help guide us through the ownership journey. All right, so before we discuss ownership, I want to talk about the stack and the heap. Okay, the stack and the heap, there are two ways that the program can use memory during runtime. What does that mean? When we create any types of variables in our code, so let me come here to code. When I write let x equals 5 here, I'm storing values in memory, okay? So that's what we mean by memory usage. First, we have the stack, which is a LIFO data structure. A LIFO data structure means that it's last in, first out, meaning that if you add an item to the stack, and then you keep on adding items, the last item that was inputted into the stack will be the first item to be removed. A good analogy when thinking about the stack is to think of a stack of plates, okay? So imagine that you have a bunch of plates and you start putting one on top of the other, on top of the other, on top of the other. The first plate that you'll be able to remove was the last one that you put on the stack. Okay, otherwise the plates fall apart. One condition that we have for keeping data in the stack is that all the data stored there must have a known fixed size, okay? This might not seem super significant as of now, but you'll see the implications that it has later. Moving on, we have the heap. What the heap does is we request the OS for a certain space in memory, and the OS gives us back a certain amount of space, which we can use for storing certain things, which you'll see in a moment can be strings and whatnot. Okay, a good analogy for thinking about the heap is arriving at a restaurant and requesting a spot. Okay, so you'll say, hello, I have 5 friends and we want a spot in your restaurant, and then the person serving you will then go look for a table with 5 spots available. Okay. Well, obviously, pushing to the stack is faster than allocating to the heap, because for the heap we actually have to go look for space. While for the stack, we just push it onto the stack. This notice the wording that I'm using here, pushing onto the stack. Okay, that's important notation. Well, not notation, terminology, I should say. Yeah, so pushing to the stack is faster than allocating to the heap. Same thing for accessing data on the stack is lower than accessing data. Sorry, I think here I meant to say the opposite. Accessing data on the heap is lower than accessing data on the stack, because we have no need to follow a pointer on the heap. Okay, so this is reversed. Let me add a little comment here. It's faster to access data on the stack. All right. Moving on. When we call a function, the values passed into the function and the function's local variables get pushed onto the stack as well. And when we're done, also notice on my terminology, when we're done and we leave the function's scope, they get popped off. Okay? Alright, so before we get into some more details of ownership, let's establish the basic rules. Each value in Rust has a variable that it's called its owner. Okay, so going back to the code that we wrote previously, when we have let x equals 5, x is our variable, and we're binding the value 5 to x. Okay, so 5 is owned by x, right? There can only be one owner at a time. This is a very significant statement, which you'll understand more by the end of this video. When the owner goes out of scope, range where an item is valued, the value will be dropped. Dropped is also important terminology here, but it won't come into play as of now with these basic variables that we're using. But what that means is that right here, x is no longer valid. Okay? Alright. Now, to better explain ownership, it's important to introduce the string type. If you're also following along in the book, and probably in some older video, I've probably introduced strings. If you look at the 12 Days of Christmas extra problem as well, that was just a bunch of strings. But in any case, you've probably seen strings before. Also, if you have any experience with any other programming languages, string is one of the most basic data types that you'll be using. But in Rust, we have two string data types. We have the string literal, and we have, well, the string. Okay? They have very fundamental differences in how they're set up, meaning that, well, the string literal cannot be mutated. Okay? So we cannot concatenate. It must be hard-coded, and it is stored into the program binary. Whenever we have Rust code and we compile it, so we run cargo run or cargo build or cargo check, our code is converted into zeros and ones. These zeros and ones are called the program binary. The string literal is hard-coded onto the program binary. Okay, so it's neither stored in the stack nor the heap is stored in the program binary itself, hard-coded in it. Okay, when I say that the string literal cannot be mutated, I mean, oh, this was me making the summary. I mean that if we have let s equals OK, I can still do s equals OK2. This is not what I mean by mutating. What I mean is that I cannot do something like s equals s plus how about you. Okay, we can't do that. Okay, however, with the string type we can, and the main reason why we can is because the string type is stored in the heap. Okay, so we request the OS for memory space during runtime. The string doesn't need to be hard-coded, so we can get input-output from the user, and we can mutate it. So right here, you see the example that I showed previously in the code. You can push items to the string, which is concatenating, if you're familiar from other programming languages, and then we can print this. Okay, so I can probably, oops, I'm highlighting. I can probably copy this. Let's paste it right here. Now, if I run the code, let me clear this. Let's do cargo run. We get a bunch of errors. Stop push. Cannot borrow as mutable. Consider changing this to be mutable. Oh, sorry. Well, of course, we still have to make s mutable. Otherwise, we're making it an immutable variable, and it cannot be changed. All right. So if we run cargo run right now, we're finished, and we get hello world. And s was initially instantiated to be just hello, or the hello value was binded to s to be just hello. Okay, so just a little side note, these two little guys, they allow us to grab from the from function from string. Okay, so whenever you're gonna store a string in your program using the string construct or data type, you're gonna be using string, these two little guys, from. Okay. Now to utilize the heap, we must 1. Request memory from the operating system at runtime. So that's just done by string from. And 2, we have to return the memory to the OS when we're done. If you're familiar from other programming languages like Java, we have a garbage collector. What a garbage collector does is it continuously checks if variables are no longer being used. So if their values are garbage, it collects that garbage. All right. But languages without a garbage collector make it the responsibility of the programmer to identify where the memory is no longer being used, and then return this memory, so we're not wasting space in the OS. However, Rust takes a different approach to this, and what it does is it automatically returns the space the memory was using when the variable goes out of scope. So you can see right here, we created S, and as soon as we leave, assume that we have here the function main, as soon as we leave the main, S is no longer valid. So right here, we would have what we call a drop. So the value of S is being dropped by Rust. Oh, actually, I say it right here. So Rust calls a drop function. All right. Now let's get into the interesting stuff. Ways the variables and data can interact. Let's start off with move. So when we create two variables, x and y, as I mentioned previously, we're binding 5 to x, and then here we're creating a copy of x and binding it to y. Okay, so if you imagine the stack, we create a x, let's say 5, and then we create a copy of x, put it into y, put a y in the stack. With strings, you might think that we're doing the exact same thing, but in fact, it's, well, very different. And to show you that, I've downloaded a neat app which allows me to draw. I'm gonna draw how this is all happening. Okay. So we created. Okay, to start off, let's say, I'm not gonna be super perfectionist on this, but whenever we create strings, we're creating actually 3 values. Okay, we're creating a pointer, we're creating a length, and we're creating capacity. The difference between length and capacity is not gonna come into play right now, so you can just ignore it for now. But length and capacity and a pointer. Okay, so here we're creating S1, and we're allocating S1 a place in the heap. Okay, so let's create the heap right here. To make it easy, let's say that the heap value, our string is just OK. So here's the index number, here's the value in that index. So if we have OK at index 0, we have O. Index 1, we have K. Now, when we create a second string, you might think, well, if you apply the same logic that we had from the two x and y, oh my god, that doesn't look like an x and y at all, but if you apply the same logic that we had in x and y, we would create another instance of this in the heap. So we would copy this heap value and then point. Actually, I missed this. The pointer is pointing right here. We would create another instance of this, and let me see if I can copy it. I cannot copy it, never mind. Okay, well, pretend I did copy it. We would place it right here. Okay, so this is the copy of that. But in fact, we don't do that. What we do is we just grab the pointer. So we're going to call them P, L, and C. We're going to grab the pointer and point it to the same place that S1 is pointing in the heap. Okay? But this, as you can see, is going to create some problems. Because if you remember, so let me go back into the code. I'm going to create an S1. I'm going to remove this part of the code. I'm going to create now the S2. I'm going to set up S1, S2 to be equal to S1. So right here, S1 comes into scope. Go to the next line. S1 comes into scope. Here, S2 comes into scope. And S1 pointer of S2 points to S1. Okay. But what would happen, let me just delete this X. What will happen when we leave the scope? Are we gonna drop for both of them? So drop the heap location for S1 and S2? That creates a problem, which is called a double free error. Because we're trying to free the exact same location in the heap twice. Alright, so that creates a problem, and Rust fixes that problem by, drumroll, ownership. Woo! We got there. Rust solved that problem by ownership. What that means is that right here, the value of S1 is moved to S2. Okay? What that means is that right here, if I try to print S1, I'm going to get an error saying the value of S1 was borrowed here after move. Okay, so S1 no longer exists. S1 got moved onto S2, or S1 transferred ownership of its binded value to S2. Okay? So, mostly, that's ownership. Let's just go through it, see if we didn't miss anything. In this case, we're allocating S1, which consists of a pointer, length, and capacity. Oh, the pointer, length, capacity, they're all stored in the stack, okay, because they're fixed length. And S1, and the value, actual data of S1 is stored in the heap. And we're setting the S2's pointer to S1. As I said, we're not copying the heap data, so we're not creating another instance of this. Here's the double free error I mentioned. To avoid this, Rust considers the value of S1 to no longer be valid. Right, so that generates an error. Now, what if we want to keep the value of S1? In this case, we use cloning. We set S1 s1.clone, and then s1 can still be printed. Right? Now, you notice that for these previous values, so x and y, we didn't do cloning. And that's because they have a copy trait, which actually you can notice in one of the error messages right here. So move occurs because s1 has type string, which does not implement the copy trait. What the copy trait means is that whenever you assign a value from the left-hand side to someone's right-hand side, it will not be moved, but rather it will be copied, maintaining the value in the initial instance. Okay. So the copy trait is implemented in integers, bools, floats, chars, and tuples. Another interesting part is ownership and functions. When we pass a variable to a function, we are giving ownership of our variable's data to that function. So if you see this code right here, we create a string s, and we pass its value onto this function. So s is moved to this function. Right here, s1, which is the parameter to the function, gets in the scope, and then we just print it. Oops, sorry, that should be an s1. Rust calls the drop function here, and s1 is cleaned. But notice here, because we passed the ownership of s to the function, s is no longer valid here. So we gave the value of s to the function. However, with integers, we can pass into the functions and be fine, okay? In comparison, when we leave the scope, integers are just popped off the stack. Return values can also give ownership. I copy now this code directly from the book. It gives very detailed explanations on what's happening in each step of the code. But pretty much what we have to get from this is that in this function, we are returning some string, and we're setting the value to s1, okay? So s1 is being given ownership by a function. So we don't just give ownership from variables, we can also give ownership from functions. But now you might be thinking, okay, this is super annoying, right? I'm gonna pass the value of my variable onto the function every single time, and then I just lost the variable. I can't use it anymore. And Rust architects thought about that, and there's a feature for that which we're going to talk about in the next video, because I think this video is getting huge. So thank you so much for watching. I hope you enjoyed, and I hope to see you next time. Bye bye.